This should be interesting to most of you because here we are summarizing in a few minutes, in a few slides, some of the key things that you can do to make sure that the software, the simulation software can give you accurate results in a short amount of time. You can avoid some pitfalls, okay, and you can get the best out of it in general. So specifically, we will look at what are the possible errors or best practices considering the part model, okay, followed by how do you optimize accuracy and speed, and finally a little bit about how do you manage the project files, because these programs can generate gigabytes of information, and if you don't manage them properly, you have problems. So just a few tips, good practices about how to handle all these things. To start with, always remember that when you say simulation, simulation is the last step or the third step in the process, and before which you need two other things. Before you even think of simulation, you need to create a 3D model of the part, ideally as cast part. Without that, you can't even think about simulation. Either you have to model, or you have to get it done by a local CAD agency, or if you have a good relation with your customer, ask the customer to send you the part drawing in 3 dimensions as a 3D CAD model. Now that is also not enough, because that is usually a machine drawing. You have to still convert that into a casting model, which means add allowances, all those things. Now you need not add all allowances, at least machining allowance and shrinkage allowance if you can add, it's a good starting point. Okay, and remove the drilled holes. So we'll look at some of those guidelines. And more importantly, add the gates and risers, because without gates and risers, what are you going to simulate? You need the mold cavity finally. So this is an important key step which happens between CAD and simulation. You need to do methods design. Okay, and what is methods design? You do the feeders, a parting line and cores and mold cavity layout and feeders and gating and feed aids if necessary. All these things, remember, can take a lot of time. Okay, and if you use a CAD modeling for that, God forbid, I mean you have to go back to CAD, again model, export that, go back to simulation, again go back to CAD to modeling. It can make life, the marketing presentations look very good, but real life always is different from what you see in the simulation videos. I mean you have a lot of background work to do before you can hit the simulation button. An actual simulation, as you have seen in the last lesson, you can do solidification, mold filling, and you can optimize the methoding, and if possible, if you can have some cost estimation built into the program or externally, you can link it with that, so you can see what is the best combination of quality and yield that I can achieve. Okay, so some examples of programs which can handle some of this. Obviously it's not an exhaustive list, but I have put that there. Now what are the inputs? Just quickly review. Part model inputs has to be in a standard format. It could be IGS, but most simulation programs, they ask for STL inputs. STL is one of those robust formats. It can be reasonably free of errors. It can be and it can be read, exported and imported by most programs without much problems. So it has to be, it can be an STL or IGS file. But STL files also can have problems. For example, a single missing phase can completely throw your mesh generation out of sync. The program will refuse to proceed if the STL file has any errors. So if your simulation program has any STL error fixing routine, that is a great thing to have. Then you need a material property database. Most software packages do have their own internal database of part material properties, and we have already seen what properties we want: density, specific heat, conductivity and all that, and mold properties like mold, specific heat, conductivity, density again, and few other properties like you need fluidity and you need turbulence, sorry, in fluidity you need viscosity, surface tension if possible. Some of these values are there. Some packages have them as a table of values. Some people have just 3 values: evaluate pouring temperature and liquidus and solidus and maybe room temperature. Some packages may have it as a graph, and some packages allow you to put your own values from an Excel file or a table or a graph, and they can take your values. But then you have to have a full-fledged R&D office in your foundry to generate those values of. Imagine specific heat, conductivity values generating is not easy in a foundry. Even for research lab, it is not easy. Then third main input is you need the methods design. You need to have the parting, cores, feeding, gating, mold cavity layout and so on. Remember, when I say design, not a 2D drawing, but a 3D models of all these things. Again, preferably in the STL format, either in the same package or exported and imported into simulation package. Finally, you also need the process parameters, the pouring temperature, pouring rate, and in process, the interface coefficients, we mentioned that again and again, between liquid and solid, between solid metal and the mold and the air are 3 important interfaces that you need to have values for. Finally, you also need to know what are the problems trying to solve. Okay, simulation is there, you want to drive the vehicle and it's fun, and showing the pictures off and using it for your marketing brochures is great, but end of the day you want to know what problems you really want to solve. Okay, is it shrinkage or blowhole or whatever? Do you have photographs of the actual casting with the cut sections so you can match it with that? So capturing shop floor data is equally important, and giving it to simulation team is equally important. Okay, so you need to capture the actual shop floor data and severity, location, type of defects and so on. And quickly, what kind of defects we can catch with simulation? One, with solidification we can look at microporosity. Okay, not all packages can capture microporosity, but more than half of them can look at micro also. Macro anyway, everyone can do anyway easily. Mold filling, what defects? You can catch erosion and inclusion. You can catch cold shuts and blowholes. That is with coupled simulation or mold filling simulation. Next, if you add microstructure, we can also start looking at grain size, grain distribution, and by interpreting that mechanical properties like strength and hardness. Then if you also have a stress module, you can look at stress and distortion, or possibly if the stress opens up, hot tear and cold crack. So these are the majority of defects that software packages can handle. But as you go from level 1 to 4, the skill level of the person who is using the software goes up. So by the time if you come to coupled simulation of solidification, filling, microstructure and stresses, you better think about, along with the software and hardware, a PhD humanware also. You cannot do it with a normal diploma engineer. He needs to be able to interpret and run the programs carefully. It's very complicated to handle coupled simulation of all the 4. And the requirement of correct proper database becomes even more critical. We mentioned that if the values are not very right for solidification, you still get a good result. But if the values are not right, you get completely wrong results for structure properties and hardness and stresses and so on. Okay, that is one point. Second point is, some foundries ask, okay, what about, can I predict mismatch with the software? Can I predict gas porosity with the software? There's some defects which are completely process dependent. Mismatch comes because of your mold boxes not fitting, you can't simulate that. Gas porosity comes because your degassing is not good, or melting practices or pouring holding practices are not good. It cannot be simulated in a software. Okay, so please remember that these are the limits of what simulation programs can do under ideal conditions. Real conditions, if you ask me how much matching happens with, I think someone asked this question. Actually, what is the average matching of results? Okay, and we have asked this question to everyone who uses simulation software. I asked the question to him, and my averages today is that they say, if I do 3 simulations, okay, one simulation, the results of prediction accurately match what I see on the shop floor. In another one simulation, it is useful. It doesn't match accurately, but it is useful to change or improve a methoding. And in 1 out of 3, it doesn't match at all. Simulation, you have what is called as false negatives or false positives. False negative means the program says there is a defect, actual casting there is no defect, which is actually happy, but you are wasting your time. Or a false positive, the software says there is no defect, casting is clean, but actual casting is a defect. So both these can happen in at least 1 out of 3 cases. That's the averages, what I have heard from various people.
What is the main reason?
The databases. The main culprit I told you was the property values. We do not have the accurate values of thermophysical properties as a function of temperature for our materials, our molding conditions, our grain size, our sand grain size and so on.
Europe and Germany and Japan for that matter, they have done a lot of...
Yeah, but that is tuned for their databases. They have good research labs. So we don't have any national, you need a national mission in India to generate values of that, so our simulation programs can benefit from that. But we are very happy to see that this new technique, the GVM and all that, coupled with this smart way of using the industry information to put into physics, is giving us not only fast, high speed, but also better accuracy. So let's continue with the best practices. So typically you must have the photograph of a defective casting before you start looking at simulation and all that, if it's existing part. And then you keep changing the methoding design, you try different layouts and then see which layout works out fine. Now how do you get accurate results? Rule number 1, and you see the picture here, between the hole is supposed to be drilled. So if you simulate with the hole, you are simulating the wrong part. So you should remove the hole and then you should simulate the casting, and the results are totally different if you see in those two pictures. So don't simulate machined casting, simulate as cast part, okay, fundamental. And also I mentioned that the mesh size has to be less than half of the minimum wall thickness in the part. So somehow find minimum wall thickness by drawing, by measurement or whatever, and then make sure mesh size is less than half of that. Fortunately, what we have done is we have automated this also. The program automatically finds minimum wall thickness, automatically sets the right optimal mesh size, so you don't have to even worry about that. Otherwise, at least other packages you can look at that. Then the last is heat transfer coefficients. This is something which no one can solve the problem. You have to do trial and error. There is no option, there is no scope, no escape from that. You try some IHTC value if it's in database of the software. If the results match, well and good, continue with that. If the results don't match, fine tune that, do it again. So you have to have a small R&D office along with the software to keep trying out and finding out over a period of year or so. For the metals which you produce in your foundry with the processes, you should be able to figure out what values of IHTC give me good matching between prediction and observation. Okay, that is no escape from that. Let's just take 2, 3 things. Let's say sand, grain size and moisture content, let's say. These are inputs on the shop floor. But the programs do not have these as inputs. The program inputs is only the density in this connection, the density of the mold and the heat transfer or let's say conductivity of the mold. Now you know that if you add moisture, more moisture, less moisture, conductivity will change. Even the grain size and compaction will change. But the programs cannot take those as inputs. And extending your question further, if you say I am going to add little more silicon, little more magnesium, can the simulation program take that as input? Again, answer is no. The simulation program inputs are only the thermophysical properties of the material, which is conductivity, specific heat, density and viscosity and so on. So unless you have a lab which can establish a graph where if I change the moisture like this, my density changes like that, K changes like that, and that graph is input in the program, which requires a good engineer and I said PhD, it's not possible to do that. And finally, if you see that your prediction and actual results don't match, false positive or false negative, if it doesn't match, don't jump suddenly to conclusion. Go and check. Okay, you put a feeder size of 30 millimeters here. You go and check, is it 30 millimeter shop floor? You will find that the methering engineer shop floor, he says, no, I know better, he'll make it 35. And you don't know. And then you say, okay, results are not matching. So you have to actually find or check that what was simulated and what was actually put on shop floor, are they exactly same or not? Even a small mold coating, which you don't put in simulation, but in actual casting you put a mold coating, even thickness of mold coating can alter your results. And I told you neck, even a small change in neck size of 5-10% can totally alter your porosity picture in the casting. So verify whether both are same. Now how do you save computation time? If I put in a common sense kind of equation, total computation time is equal to number of times you simulate into time per simulation. So if you are smart, you should reduce both. Reduce the number of iterations and try to reduce computation per iteration. How do you do that? Number of iterations reduction, the golden rule is start from a good first design. If you start from a very wrong place of feeder or a wrong size of feeder, completely wrong size of feeder, okay, or gating position, I mean you are going to take 5-10 iterations just to come to a good design. Okay. The next thing to reduce the computation time is to reduce the part file size, not part size but part file size. Okay. And you see an example here. Both are the same part, except there is a slight difference in the visualization of that. You see that the first part has fillets. In the second model of the same part, the small fillets have been removed. If you remember our STL file, we said STL file is simple triangle language, right? You are dividing the casting into triangles. And there are more triangles whenever you have curved surfaces. A fillet is a curved surface. It's a small curved surface, but it can generate thousands of triangles and each of them has to be stored. Now that doesn't add anything to your computational accuracy, because anyway you're going to mesh generation, and whether the fillet is there or not there, you're anyway going to have a small, your brick element there. So you can happily remove small fillets from your part model, thereby reduce the part size by, if you see, as much by 90%, 1/10 of the original file size. From 4 MB it has come down to less than half MB. Okay. So by these small tricks, just by removing small fillets, if it's possible to edit. Sometimes the customer sends you the STL file, then you can't edit. But if he sends you a step file or a IGS file, you can go back, edit the file, remove small fillets, and thereby reduce your computation time dramatically. Because mesh generation, computation, all those things depends on the number of cells. So you can use this trick to, at least sometimes you can reduce by half the computation time. Okay. And the next smart trick you can use a bigger mesh size for initial iterations. Okay, you are still figuring it out where to put the gate, where to put the riser, what is the initial feeder size. Okay, use a big size. Use same as wall thickness, part wall thickness. Part wall thickness is 2 millimeters. Use 2 millimeter mesh size, no problem. And then one final run you can do it at 0.2 millimeter or 0.5 millimeter mesh size. So do initial run with large mesh, do a final run with small mesh size. It's a simple tricks like that can save you a lot of computation time. Okay, data is king these days, right? I mean, so you have to worry about your input files, you have to worry about your output files. And output files can be all this temperature as a function of time at different locations in the casting, and you may have videos of mold filling and solidification and so on.
Actually, the input, suppose I have to put some wrong input inside the simulation process. Suppose I have put the wrong feeder or wrong gating or the wrong spacing of the gating. Will the software correct me?
No. Because I also assume that what you want to do, you know what you want to do and you have given that input. It can only warn you if you have put the gate outside the mold, which you can't put in a real life, but in a mathematical model you can do anything. That it can warn you, those mistakes it can error.
Correct me that
No. But the indirect answer is right. Yes, the moment you do simulation you find that, hey, this is shrinkage is coming in the casting, feeder is not working. So immediately visually you know that feeder is not working and you correct it. So whole idea of simulation is you design, model, simulate, interpret, again redesign, model, simulate, interpret, and this is called as iteration. This iteration, and the whole idea we're talking about is how do you reduce the number of iterations, how to reduce the total time per iteration and so on. So as I mentioned earlier, in most packages the methoding is not done, only it does simulation. So you do methoding on paper, then you go to a CAD program to do the methoding, modeling of those feeders and gating, export that, import it simulation, again go back and do that. That takes a lot of time because you have to switch on and off many programs. There's one more thing which we tried to, when initially itself people said, sir, this is a big pain. So we said, okay, let's combine both. So methoding and modeling and simulation and costing also, everything I put in one framework. That saves you a total time of iteration. Okay, data, we have to also do little tricks. You may have something like maybe 100 files in a project. You may have the part model and then the feeder model and then the mold model and core model and then your filling results and solidification results and some videos, all those things. And we have some defect photographs. So all those files, eventually within a few months, you will find you have now thousands of files and you don't want to delete any files. So one of the first things I tell people is have a standardized naming convention. If you are making a butterfly valve for, let us say, some particular customer ABC, so say BV or is a 100 diameter BV 100 for so this customer ABC, and put the name and use the same name for all the files. So you can say BV 100 ABC dash inputs dash part model dash video dot this thing for dot MPEG or JPEG. So you try to have a similar file name, because otherwise you will find it's a nightmare to find out which file was used in which project and all that, and preferably put them in a single folder with the same name again. So I'm saying this because now we have handled, I don't know, I lost count, maybe more than 1,000 projects at IIT Bombay over the last 10-15 years. And if you tell me what you did in 2000 for this company, I can go pull out exactly that picture or that defect photograph or whatever it is. I have no problem with that. And of course I also back it up nicely, because if you don't back up in this age of virus, earlier hard disk failure was a big problem, floppy failure was a big problem. Now those problems are solved, but now you have virus problem. Suddenly you will find your flash drive had all the files, suddenly you see it's all virus only, nothing else is there. Right? So you have to worry about backup, clean virus check and backup. One of the things, smart things I do is in my computer I have 2 hard disks. That's one way, because that is, and also have, can you imagine, I have 4 backup hard disks, external backups. Sometimes I get confused which is the latest one, but I have figured out, I have standardized all my life. So many times my computer has failed. Many times my computer has failed, but I have had no problems, my life is back. So you have to have good practices for managing your data, backing up, keeping only those files which you need. Regular systematic backup at least once in a week is mandatory. Anything more than that is criminal. And finally, not to worry about security. Many times this data is exchanging many hands. With your OEM you may have signed a non-disclosure agreement, then you give the data to a simulation consultant, or you are sending it to Foundry. Remember, you have signed an NDA, but you have not signed NDA with the person who you are changing with. You are in trouble if something goes wrong. Actually, we Indians trust each other a lot, and things usually don't go wrong. But now your customers who are abroad, they insist on that. It's part of the documentation process. So you have a standardized MOU, a standardized NDA, which you can electronically sign. You don't have to worry about physical signature anymore. You can have a scan your signature, put it into a doc file, make a PDF, send it across. So you can automate the process, you can streamline the process, you can save time in that. So to summarize, in this session we looked at the different elements of simulation, and we not to forget, you need to have CAD model and methods designed before you hit simulation. We also looked at how do you improve your accuracy and reduce your speed and manage your data, okay, for a particular simulation package. And then you have to do it in a systematic way, disciplined way, day after day, month after month. Okay. So that's we stop here.